Okay. So I've started that recording. Logan is asking about the assessment date. Yes, Logan, it's this week. So a couple of reminders for everybody. So this week is your assessment. It will, like it always does, typical process. So we will open it. I'll open it on Wednesday morning. And then you'll have until Friday at noon, middle of the day on Friday to do it. It will cover essentially units 4, 5, and 6 in your Canvas. So instead of clustering them all together as one unit, I separated them. So momentum and energy concepts that we dealt with, fluids and matter, so all the stuff from matter and fluids, and then however far we get, probably through, maybe we'll talk about capacitors, I'm not sure, on electricity. So that assessment will open on Wednesday, and obviously we won't necessarily have all the content on Wednesday, so you probably won't want to start it Wednesday before class. We'll have a little bit of that content on Wednesday, very basic. We might get through it today. We might just bag the rest of it. The other thing that I wanted to make sure you're all aware of is, so we're, technically going remote. After Thanksgiving, it doesn't really change anything. We're remote now. Whether or not I'm come to campus to record, or whether we do it from my office in my house, probably gonna be coming to campus, but we might, I might do it from home. Regardless, it doesn't change anything about you. So we'll still have synchronous classes. We'll still have, all the same things. So for our class, it should really look no different for you in terms of the fact that we're going remote after Thanksgiving. Okay, there's another question that came up. Ben is asking why the time the weekly practice closes changes every week. It shouldn't. It should be 9 o'clock on Monday. But I'm not sure why it's different. Isn't it always 9 o'clock on Monday? It was 8 today. Well, that was just a mistake. So go ahead and do it. That's fine if you didn't get it in before 9. It's really better to do those on like Friday, but I'm not sure why it was 8. It must have been I must have the wrong number. I don't know if it's been changing every week or just was this week. So if you were waiting to do the weekly practice until 8 today and you didn't get it in because it was normally due on 9, just send me an email and we'll do it after the answers are in. And I think it's still accessible, so we'll get it taken care of. No big deal. No, that's not sure. So the assessment, end of the term, we will just have optics for the end. So we will start optics on Monday, and then Monday there's no class on Wednesday. So next week, no class of Wednesday next week, and then just for the topics, I don't have one. No, I can't get into the studio. There are so many, so, okay. Hold that question. Let me finish my first train of thought. I get too distracted when the questions come in. Okay, so we're starting optics on Monday. And that will take us through to the end of the term. We do not have class on Wednesday of Thanksgiving week. That's not a school day. And so we just start Monday, and then we'll pick it up again on the 30th. And we have 2 weeks, and that's it. And then you'll have your last assessment. We will go over the final exam after Thanksgiving, how that looks, how you sign up for it, because you have to sign up for it early. But you'll have up through this third assessment to pick those topics. Just as a heads up, as you move into the optics unit, you will not get to choose those topics for your redemption. So it's too close to the timeline. So that is only offered for that single test. So you do not get to redeem yourself on those concepts on the final. So once you know how you did on this week's assessment, you will be ready to decide what you want to do for the final exam. And I do have you sign up for that well in advance of the final exam, because just as a reminder, it's personalized for each one of you. So it takes me a significant amount of time to make every person's test individual. So because of that, I make you sign up pretty far in advance, like a week or two in advance. So start thinking about, over Thanksgiving, start thinking about what assessment elements you're going to want to do from the first 2 assessments. And then you'll get your test back on this 3rd one, and you'll just have to make a decision on the 3rd one, so you're ready to make that decision and sign up for the final. Okay, so there was a question about mini lectures for the topics. There will not be any mini lectures for the electricity topic, and there weren't for buoyancy and fluids, so you will have to sort of cut through the main lecture. There are some, I just couldn't get into the lab. There are some mini lectures for optics, because I did some of those at the beginning of the term in preparation for being remote like this, but I didn't know we would be doing fluids and electricity, so I did not do that. So it'll say, just like it has this week, check the lecture, so you're just going to have to kind of fast forward to find those pieces. All right, other questions? I'm just peeking, and I have talked to you about the weekly practice that did exist. Okay, so you guys did really good on the weekly practice. There was a mistake on one of the answers, so I just marked the wrong one. It had to do with, let me pull it up. It had to do with a positively charged particle. So it was, which of the following objects repel a positively charged particle? The vast majority of you nicely put that a positively charged particle repels a positively charged particle. That is the right answer. It was marked wrong in Canvas. So again, it doesn't matter that you get one wrong. I will change the answer key. I must have just then, it looks like it was marked for the first answer, and that's the default answer on Canvas, so it just didn't get reselected when I was plugging in that question. So it is, in fact, a positively charged particle repels a positively charged particle. A negatively charged particle does attract, and a neutral charged particle, remember, also attracts to a positively charged particle. And so that one is, it was just, the wrong answer was marked in Canvas. So that'll be fine, and it'll be fixed on the answer key when you use it to study. And of course, it doesn't matter, your grade doesn't matter on the weekly practices. So I don't know if it updates it automatically. It might, but again, they don't matter. All right. Any other questions before we get to our quick review and then our new stuff? We aren't going to go into breakout rooms on the weekly practices because they were all really good. So. Okay, then we are going to do just a brief review of static electricity, this idea of positives and negatives, and I'm going to turn the turn the camera, and hopefully we can zoom in. And then there we go. And so you should see. Well, hopefully you can see it. I'll move the card a little bit. You cannot see my little, these guys, say so in the chat really fast. I'll hold them up too. Okay, so we talked about a few things on Wednesday. We talked about this idea of positive and negative charges and how they interact with each other, neutral charges and how they interact with both, and we did some fun examples with that, and then how things get charged. So we're just going to do a real quick review of all those because I told you I had some really fun sort of demos at campus, but I was at home because of the weather. So let's talk a little bit about what those are. So first, it was how do we get things to charge? And we have 3 methods to get things to charge. The first was violent scuffing, ripping electrons off. So I have a composite rod and some fur. And if I rub the two together, I can strip off electrons, and I can make both the fur charged and the rod. So if I'm stripping electrons off of the fur onto the rod, my rod now has more electrons. My fur is left with fewer electrons. So the rod becomes negative, and the fur is positive. So that was one way we made a charged object. The second way we got a charged object is if I had a conductor. Now remember, a conductor was a material that electrons could flow freely through. There's a whole bunch of extra electrons on this rod, and those electrons, they want to spread out because they don't like each other, right? Same, electrons are negative, they repel. So when they have the opportunity to spread out, they will spread out. And so I can put them on top of this metal conductor. I'm rubbing the rod on top of this metal conductor, and the electrons by conduction are going from the rod to that metal conductor. Now, they are also flowing, spreading out, because electrons like to spread out. They're also flowing into the strings, and our strings are spreading out. Again, electrons like to spread out. Now, the rod doesn't transfer all of the electrons. It's still negatively charged. So if I were to bring this negatively charged rod near this negatively charged little guy, we should see it repel, and we do. We can see that the strings are going to repel from the negatively charged rod. Hopefully you can see that. I'll probably bring it closer to the camera because it's super fun. Okay, so they're going to repel. But my hand is neutrally charged, right? And negative charges and positive charges like to go towards a neutral charge. So here, or we can see that the neutral charge attracts. Okay, so spread out by conduction contact. Now, if I take a piece of plastic, this type of plastic, and wool, and I strip them together, remember I mentioned to you that depends on which of the materials is easy to get electrons off and which of the material is more difficult to get electrons off. Well, in this case, the electrons are stripped from the bar, put onto the wool, and I can also take more electrons from, come on, oh, you're not gonna play with me today? I can make more electrons from the bar, easily taking off to get onto the conductor here. So I have a similar little hairy dude. I'm gonna take more electrons off the bar and put them onto the hairy guy. Okay. All right, so now this guy should be negatively charged, and we can see that these two are repelling one another, okay? Why do they both spread out? Well, they're both negatively charged, and they both want to get away from each other. That being said, I told you that I'm taking electrons off. Electrons easily come off of this rod, so it's positively charged, and we see an attraction for both of these to the positively charged rod. All right, so positives and negatives repel each other, positives and negatives attract, likes repel one another, and neutrals attract to either. Okay. The other type, and so we did two types of charging a particle. We did the fast friction, the violent stripping electrons off, and then we did the conduction. We just have to touch it to a conductive material and the electrons will flow freely. The last type was that induction idea. So what I have to show induction is what we call an electroscope. So what we have here is a conductor. That conductor is connected to two metal foils, also conductors, okay? And right now they're hanging loose. So they're pretty loose. All right, so we know that a charged particle, okay, so if let's see if I can get it charged enough. It's not as dry in here as I usually like, but, okay, so I am bringing the rod close to the conductor, and we see that the two leaves Kind of see how they spread apart a little bit. There we go. The two leaves spread apart. That is that charge. So I'm not touching it. I'm just bringing it close. We're spreading apart due to that induced charge idea. All right, so those are our three ways that we get charged particles and how they behave with each other. So, quick questions on any of that while I turn us back to the front, and we're going to move to actually quantifying some of those interactions. All right. So I have the question, do opposite charges attract more intensely than neutral charges, or the attraction force is the same? Good question. Actually, Christian, we're going to talk a little bit about that. Neutral charges attract, remember, due to that polarization idea. So depending on how, it all is going to depend on how manipulative those molecules are. So in a water molecule, for example, it's very easy to shift the hydrogen and the oxygen relative to one another. So because of that ease, the intermolecular forces are a little weaker, and so we'll get a stronger attraction with a water molecule. Whereas if I rub the balloon against my head and I stick it against the wall, that's going to be a little weaker attraction because the molecules in the wall are a little harder to manipulate to rotate. In terms of positives and negative point charges, so single charge objects, there's going to be the strength of the charge, we're going to find out, strength of the charge and how far apart they are certainly going to play a role in how large that force is. So it's not as simple as they repel or attract one another. There is a strength associated with how much they attract or repel for both charged particle interactions and neutral and charged particle interactions. And then the additional piece with the neutral interactions is how easily it is to manipulate the molecular interaction, the intermolecular forces within that object, the solid versus the liquid, and then of course the molecules within that material and how polar those molecules are. So it's a bit more intense of a question than just a yes or no on that one. But we are going to talk about the strength of the charges with two charged particles. So we're going to shift and just look at the attraction and repulsion with charged particles for the next topic. And that topic looks at what we call Coulomb's law. I am not spelling that. And Coulomb described the exact thing that Christian was asking about, the forces, the interaction between charged particles. So we're going to look at what might influence that interaction, and you already have the understanding of some of that because you already understand Newton's second and third law. And these interactions are a little bit related to Newton's second and third law. So if we have a positive charge and a negative charge, we know that these repel one another. So our negative charge feels a force in this direction, and our positive charge feels a force in this direction. Now, what is that force the result of? Well, it's the positive charge is feeling a force by the negative charge. So this is the force by the negative charge. The negative charge is feeling a force by the positive charge. That's the force by the positive charge. Well, these are our two interacting objects. So how do those two forces have to compare? If they're the interacting objects, that's the Newton's third law pair. So the force on the positive charge by the negative charge has to equal the force by the negative charge on the positive charge. So here's the force by the negative charge on the positive charge. Here's the force by the positive charge on the negative charge. Those are our two interacting objects. They have to be equal in magnitude and opposite in direction. One's to the right, one's to the left. So this is just a property of Newton's third law. Here are two interacting objects. Does that work if I have two similar charges? Well, Newton's law better work, right? So if I have both a negative charge, yeah, I did this backwards. These are the wrong directions. Dang it. Let's just recap that. These attract one another. They're still the same magnitude. They're still the same direction in terms of Newton's third law. I just drew the arrows backwards. Okay. So if I have two negative charges, what do they do? Well, they repel each other. So we'll call this charge 1 and charge 2. So this is the force by 1, 2. And this is our force by 1. So negative charges repel each other. Positive charges attract each other. These forces need to be pointed in the other direction. How do they compare in magnitude? Well, they're the two interacting objects. So their magnitudes are equal. The force by 2 is equal to the force by 1. And they're opposite in direction. One is the opposite direction of the other. So charged particles interact just like any other Newton's third law pair. What influences how strong this interaction is? How big the force, not just like the direction that we've represented here, the attraction or the repulsion, but the strength of that force. What do we expect might happen? If I were to make charge number 1 twice as big in strength, not size, we don't care about the size, just the magnitude of the charge, really, really negative. So this is kind of negative. This is really, really negative. Do we expect that repulsion to be bigger or smaller? We probably are saying bigger, obviously bigger, right? So if I increase the charge 1, and we're going to use this lowercase q to represent the charge. If I increase the charge on 1, then I increase the force. Now these forces are equal and opposite, right? So instead of increasing this charge, what if I said, well, I didn't mean force 1 or charge 1 was bigger. I meant charge 2 was bigger. Would that influence the force? Yeah, it's going to influence it in the same way. So if I increase charge 2, I also get an increase in the force. So changing the magnitude of the force is one result of changing the magnitude of one or both charges. Similarly, if I decrease the charge on either one or both, I would decrease the force. And that doesn't matter if I'm in an attractive situation or a repulsive situation. Well, what else might influence the amount of force I get between the two? What if I take charge 2 and I bring it really close? Okay, I made it too big. I don't want to change two things at once. I bring it closer. I bring that negative charge even closer. Well, they don't like each other, so the closer they get, the more frustrated they feel, right? So as I decrease the distance, I increase the force. The closer they get, the more they want to get away from each other. The closer these two get, the happier they are, so the more they want to get closer to each other. If I take this really far away, we might imagine that, well, the further and further I get, the less and less it really even knows that that negative charge is there. Or if I take this positive charge really, really far away, the less and less it knows that that positive charge is even there. And so increasing the distance decreases the force. And these both lead to that inverse relationship between the distance between those charges and the force. The amount of charge is a direct relationship. Increase one, I get an increase in the force. And so this leads to Coulomb's law, which I'm not going to make you do the equation mathematically. I'm not going to ask you if charge 1 is this and charge 2 is that, what is the net charge, or what is the force, but I want you to understand it conceptually, and sometimes it helps to see the equation. The force, and I'm going to represent that as the magnitude of the force, so the strength of the force, we said was directly related to each charge. So Q1 and Q2, Q1 times 2Q, and inversely related to the distance between them. And it turns out it's really inverse related to the distance between them. So it's over the distance squared between the two. So even a small change in distance gives a big change in the force. And then there is a proportionality constant. It's lowercase k. That's Coulomb's constant. It is a very fixed value. Remember, we talked about how constants are fixed based on proportionality and looking at the experiment. Again, we're not going to do the equation, so you don't have to worry about what k is, but there is a Coulomb's constant. So this relationship is what gave rise, these relationships give rise to that equation. Again, you don't have to know the equation, but the relationships are important, and I appreciate some of you like to see that in equation form. So what about direction? So this was magnitude. What about direction? And direction, if we calculate the force, the direction is going to give us a positive or a negative value. So what will that look like? Well, if Q1 and Q2 are the same sign, so they're both positive, same sign, or they're both negative. If I multiply a negative times a negative, I get positive. If I multiply it by a positive times a positive, I get a positive. So if I get a positive value for my force, a positive value is repulsion. Two positive charges repel each other. Two negative charges repel each other. This is different than our rights and lefts, right? Because in this case, this would be a positive electrical force because these are repelling each other. But if I'm interested in the force on object 2, it's in the positive direction. If I'm interested in the force on charge 1, it's in the negative direction. So it's separating, similar to torque, it's separating our direction from the math, okay? And what positive and negative mean initially with calculation of the forces, repulsion, or direction. I'm looking at the physics and where the objects are located to give me the proper direction. If charge 1 is positive and charge 2 is negative, well, multiplying them together gives me a negative. Or if charge 2 is positive and charge 1 is negative, multiplying them together gives me a negative. So a calculated negative force is attraction. Okay? And again, if I want to then talk about how that object might move, how that charged particle might move, I have to look at, well, does attraction mean I'm moving to the left for charged particle 2, or I'm moving to the right for charged particle 1? All right, so these forces relate to how charged particles interact. And what I want you to remember and think about, keep in mind, is that if I increase the charge on the particle, I increase the force on either one. And if I increase the distance, I decrease the force. Or if I reduce the distance, I increase the force. That's the conceptual idea. All right, so that is our Coulomb's law idea. Questions on that? All right, think if you have any questions. And then we're going to look at some energy ideas. We're relating all of the stuff we've learned with forces and work and energy to an electrical system. Okay. All right. Well, if I have, let's imagine that I have a charged particle. Let's imagine that I have a positively charged particle. And I have a negatively charged particle that I can move. Okay, a negatively charged particle that I can move. Now, these two particles would normally be attracted to one another, right? Attracted to one another. So if I want to take this charged particle and move it away, remove it from the space of this positively charged particle, that is going to require me to apply a force to it. And if I move it, that force is being applied through a distance. And what did we say was a force applied through a distance? Well, we called that work. It's going to take work for me to move this charged particle away. Now, work was intimately tied to energy. The amount of work it took me to do was related to the amount of energy that the particle ended up having. Well, why would this particle have energy? Well, if I would release this particle, what would happen to it? It would be attracted towards that positive charge. It would change its energy. It would go from nothing, staying still, to moving, kinetic energy. So it would change its energy state. And it has the ability to change its energy state because I gave it energy by doing work on it. So it's that whole intimate relationship between work and energy. Well, what type of energy is this? Mentioned that there were two types of energy that we dealt with. One had to do with motion, kinetic energy, and the other had to do with position. This is I'm giving it energy because I'm moving it. I'm changing its position. And this separation of charge, this separation of charge is a form of potential energy that we call electric potential energy. So this is our electric potential energy, and it's the result of separating charges. Now, one of the cool things about electrical forces and energy is that those forces are like the gravity force. Now, we talked about forces in our last unit because of interactions, and most of them were touching, right? Physically contacting each other. But we've seen, especially with that induced charge idea, we have seen, and the balloon picking up the paper off my hand, that electrical forces can act through a distance, and we just gave an equation for it. So these electrical forces that are acting through a distance are similar to gravity. Remember, gravity acted without physical contact. Now, one way we describe this electrical force acting at a distance is through what's called an electric field. So imagine that I take a negatively charged particle and I place it anywhere in this space around this positive charge. Well, regardless of where I position it, it's going to feel the effect of this positive charge. And a negatively charged particle would be attracted to that positive charge. If my test particle was a positively charged particle, and when we describe electric fields, we do use a positively charged particle as our test particle, then this positively charged particle, anywhere, if I placed it here, would feel a repulsion, a force away. So you can almost imagine that, well, if I place this positively charged particle here, these two, and I fix this. Let's just imagine this is fixed. It can't move. This particle would feel a force in that direction. If I placed a positively charged particle here, it would feel a force in that direction. Here, in that direction. Here, in that direction. Here, in that direction. And we can almost see this space around this positively charged particle, where anywhere I place another positively charged particle, it would feel a force in a direction that radiates along a line that radiates out from this positive charge. If I put a positive charged particle here, it would feel a force in that direction. And this description, this is what we call an electric potential. Field. So it's this space, you can imagine if it were a field on the ground in a regular field, a grass field, that anywhere I stepped, I'd feel that force in the direction that radiates from that positive line, that positive charge. So this is our potential field, okay? Now, what this means is that if I have any kind of separation of charge, I have this potential for charge to move as a result of that field. So if I were to place a positive charge in this field, it has the potential to move. If I were to place a negative charge in this field, it also has a potential to move. It wouldn't move in that direction, but it would move towards the positively charged particle. But again, along those field lines, Now, what about a negatively charged particle? Well, a negatively charged particle, this is my negatively charged particle, and again, I use a positive test charge. So if I placed a tiny little positive charge here, it would go towards the negative charge. Tiny little positive test charge here, towards the negative charge, such that my potential field lines, my electric field lines, would go towards a negative charge particle. Again, such that if I have this field of electric potential, then I can put a charged particle, positive in this case, and it would go towards that negative charge. The negative would go away from that negative charge. But a field, charges will move within an electric field. And we can define it using point charges, because that's what we looked at with our Coulomb's law. But we have electrical structures, like a capacitor, that has positive charged plates and a negative charged plate. And there is electric field lines between them. There's an electric field within this space such that if I place a charged particle in it, that charged particle, if it's positive, will be repelled from this side and attracted to that side, right? And setting up electric potential fields are a powerful tool that we use not only to study particles, but also to utilize them. It's actually how our televisions, well, not anymore, but our old televisions would work. And we're going to get a little bit into some of that electrical motion if we get to capacitors. All right, well, why might an electric potential be important for us? Well, electric potentials get charges to move. Why might we want charges to move? That's what our whole deal with electricity is. So moving charges allows us to get a flow of electrons which we can use to power devices like light bulbs and all that sort of stuff. So we are going to look at what we think about as electricity. Oh my goodness, it's a rough day. All right, and specifically the flow, and we now know that it's the flow of electrons in a direct way. And we're going to look at what's known as direct current electricity. So we are going to shift into looking at electrical circuits. And but before we do that, we're shifting away from static electricity. Now we're going to look at electrical motion. Any questions on our ideas of static electricity, Coulomb's law, forces, or the idea of potential and how charged particles can move in a potential? Because that's the premise for our electric circuits. Okay. So here's what we're going to do. There is a worksheet in your breakout room, and I did not check before we, oh, there's a question. Ah, hang on, Ben. Oh, yes, you'll have the same usual. So Ben's asking if there's going to be exercises. You'll have your usual daily practice and extra practice. Is that what you're asking about specifically? They're not posted right now. I always see where we're going to get with the new stuff. Good, awesome. Yes, absolutely, absolutely. Okay, so hopefully you went into your breakout rooms and signed up for a breakout room. If you didn't, but it looks like you did. Okay, Kayla, I'm going to move you to group 2, and I'm going to have you start the session when you go into group 2. In your breakout rooms, there is in the breakout room worksheets, there is a, hang on, Ben, there is a worksheet on lighting a light bulb. In your groups, I want you to try to decide which, make a prediction, make a guess, whatever, which of the light bulbs you think will, oh, a lot of people are going in to sign up that didn't sign up. Aha. Which of the light bulbs you think will light. And then when we come back to our main page, your group is going to elect one person in that group to respond in the chat which of the series of light bulbs will light, which ones will light. So you're going to go in, and the worksheet, I'm getting more people added in to these breakout rooms that didn't sign up, but the worksheet is in your breakout room worksheets, and it is called Lighting the Bulb Breakout Rooms. So again, you're going to go in, and I'll tell you how long you have. You're going to go in, there's a series of pictures depicting a wire, a battery, and a light bulb. You're going to decide as a group and discuss which of those will light, that the light bulb will light. And then when we come back, one person is going to write in the chat their choices, the group's choices. Hopefully that makes sense. I just didn't set up an ideas board. So it is 10:56. So at 11:02, so that we get discussing at 11:05. It shouldn't take you a full 10 minutes. So you have about 8 minutes to go decide which of those light bulbs will light. All right, and Ben had a question. I just have to get back to the other view. It was, you're not in one. Oh, well, go get in one. Go sign up if you haven't signed up for a breakout room. Okay, there you go. Go in to the breakout room, pull that worksheet up. What light bulbs will light? We'll see if we can make some conclusions about how we get electricity to flow. Okay. Hopefully you all signed up for one. Let's look at the files. Nick, you are in group 2, right? maybe? Yes.
Yeah, I'm working on it.
Okay. All right, you guys already made your choices. All right. I'm gonna move the cart so if you get sick, close your eyes. I have to get myself so you can see our tests. Here on the table. Okay, I have one group who says 3 will light. One group says 7 and 9.
I don't lose the camera, we're gonna be in business. Good grief. Okay. I think there were 4 groups out, maybe just 3. So we got 3, we got 7, and we got 9. So 1 more group left. Let's see, do we still have groups out? I think there's 1 more group still out. Nope, everybody looks back. Okay, well, we have a debate. So somebody from, and I'm missing 1 more group. There should have been three votes. So I have 3, I have 7 and 9. What's the last group? At 6 and 4. All right, so we have literally different answers for everybody. That is fun. All right. So, well, let's test these, but let's get your ideas as to why we think some will light and some won't. So, some, based on the discussion your group had, somebody be brave and unmute and give me some ideas as to why you made the choices that you made. Who's gonna be brave?
We were in group 2 and we decided that all of the ones that were connected to both positive and negative could work. So we thought 3 would work, 7 would work, 9 would work, and then we were deciding, we were curious about 6 and 4. That's why I put those in.
Okay.
Because they both look like they're connected to positive and negative, but they're in different placements.
Okay.
So, no.
Good. I don't have any idea who's talking. Who's talking?
Ben Larson.
Ben. All right. So one idea, and I know you can't see what I'm writing on the board, and that's fine, is that, and if I understood it correctly, Ben, your group talked about the positive and minus of what looks like a battery in the picture, right?
Yeah.
Okay.
If they're connected to both positive and negative, then we thought that they'd work.
Okay. All right. So connected to both sides of the battery, the positive side and the negative side. I just want to write down those ideas. Okay, excellent. So other ideas. So that you said you were debating 6 and 4, 3, 2 is also connected. Why did your group rule out 2?
It kind of looks like the one wire is connected to both positive and negative, so that would be a complete circuit, but there's nothing in between. Like the wire that's connected to the light isn't a complete circuit.
Okay. And so we're just developing these ideas, and then your group must have ruled out 5 as well. Is that for the same reason?
Yeah, that looks like there's 2 wires that don't make a complete circuit. It kind of,
okay.
The ones connected to the bulb look like they just roll all the way around.
Okay, all
So
right.
some that are sticking out look like they're connected to nothing. The bulb looks like it's only touching positive.
Okay. Nice. Thank you, Ben. Any other ideas from the other groups? It still looks like I might be missing a vote group, but other ideas from the other groups that led to, let's see, 3 is that positive and negative idea, 6, 7, somebody put 9, 4 also connected to both. So any other ideas from folks?
Yeah, can you hear me?
I can, yes.
Okay, we said 3 just because it creates a full circuit. As we discussed, we also talked about 7 and 9 being very similar in having that full circuit, except we looked at where it's attached on the bulb and the location is different, which is why we rolled out those 2 as well as 6, for example, because they're not like attached at the very base where the electricity input would be.
Okay, good. I like it. So I'm just going to write that down. So this idea, you bring up this full circuit idea, and then it sounds like the base of the bulb you thought must be important. Is that accurate representation?
Yeah.
Okay. All right. Thank you. Any other ideas before we do some of these tests? All good intuitions. We're gonna hone in on them, but they're all good intuitions. Okay. All right, hearing none, I'm gonna try to, I'm gonna go back to here. All right, we're gonna, oops, wrong way. Okay, so I have a, I'm gonna not worry about that one. All right, so I have a battery. And just because I need more than one hand to actually do this, and of course, if you'd been in class, you'd have all had, oops, I don't want that going. You'd all had your own to test. But so I have, here's my bulb, and the end is what, I don't know who was just talking, but who was just talking? Somebody's gonna unmute on me. All right, Mom, thank you. Okay, so the end is where that group was saying is important. And then my battery setup, so this is just holding, it's just a battery holder. So one end is negative and one end is positive. You can even read the little positive there. And this is just allowing me to hold that battery and connect to that positive and negative. So let's just quickly go through all of them. Just to make sure that the ones that you think don't light actually don't light. The ones that we might think light actually do light. It's might not be a bad idea to write these down, and you can review them. You always have access to that. So for item number 1, and actually I'm just going to pull out another battery because I don't even need a wire for that one. So here's object 1 or setup 1, and if I just put the bottom of the light to the battery, of course, we see no lighting. So orientation number 1 does not work. So good job on orientation number 1 not working. Orientation number 2, we have a wire going from the positive side to the bottom of the bulb, right? So there it is, connected to the bottom of the bulb. And from the bottom of the battery, the negative side of the battery, to the positive side of the bulb. And I have to do this very quickly, and nothing lights up that either. Now, if you were doing this in class, this wire would end up getting very, very warm on you. So we'll talk about that later in our discussion as well. All right, item number 3 was one that people thought might work. So in this case, we have the positive going to the bottom of the bulb. So I'm gonna connect that to the bottom of the bulb. So I'm touching the positive end to the bottom of the bulb. And let's see if I can hold this. And the negative side also going to the bottom of the bulb. So we're gonna test both bottoms of the bulb. And what do we see if I touch the bottom of the bulb for both of these? Does not light up. So number 3 does not work. Okay, if I touch both bottoms of the bulb. We're gonna see how we can wrestle with that idea. That's a very common one for the reasons you all mentioned. So we're gonna have to fine tune these reasons a little bit. All right, number 4. Number 4 is touching the top of the bulb. So I'm gonna try to do this not in the holder to have the extra wire. So the bottom of the bulb is touching the top of the battery, like that. And I need to get a different wire. The bottom of the battery, I have a wire that I'm gonna, it's hard to do. The bottom of the battery is gonna touch, the side of the bulb. So we have the bottom of the battery. I'm gonna touch this like this. And hopefully this is not easy. I really need a helper today. I should have been at home. Then I could have at least brought one of my kids up to help me. All right. The suspense, I'm sure, is killing you all. Okay, do we see it? It's lighting. I can't hold it much longer. So, bottom of the battery, touching a wire. Bottom of the bulb is touching the top of the battery, and the wire is touching the side of the bulb. When we do that, oh, I'm gonna get that bottom touching. We see the bulb light up. So 4 works. 4 works. Right? 5 is the bottom of the battery. And you were right who was describing it to me, that bottom just goes to the top. I'm not going to be able to show those 2 random wires out, but the bottom goes to the top. This is very similar to, I hope you can see that. I can't even see if you can see it. 3, in that the bottom goes to the top in a loop and the bulb goes to the top. So we get nothing, no lit bulb. And if I had another wire, you'd see the same thing. And again, this wire is getting very warm. All right, so that didn't work. 6 is another one. Now, in this case, I'm going to use the battery holder. So in 6, we have the negative side of the battery touching the glass of the bulb, and the positive side of the battery touching the bottom. Nothing. So 6 does not work. 7 has the positive side. Oh, I did that backwards, but here, positive side of the bulb of the battery touching the glass and the negative side touching the bottom. So this was 6. So that doesn't work. 7 has both ends of the battery touching the side of the bulb, not the glass, but the side where the little screw part is. And that doesn't work. 8 has the positive side of the battery just touching the bulb. And that doesn't work. 9, I'm not sure what difference is between 9 and 7. There isn't a difference between 9 and 7. It's just meant to orient differently. So again, we already know 7 doesn't work, so 9 also does not work. And 10 is exactly like, well, not exactly. It's like 3, but without a wire. So we have 10 is the bottom of the bulb, the one I did earlier. So the battery goes from the bottom of the bulb to the top of the bulb. The wire goes from the bottom of the battery to the top of the battery, and the bulb sits on top. But it's just the opposite side. And again, this is getting very warm, but this is not lighting. So the only one on that whole sheet that worked was 4. So just let's recap what 4 looks like. 4 had the wire going from the bottom, the positive side of the battery. I had it upside down. We'll see if this one works. So the positive side of the battery, the wire goes from the positive side of the battery. The bulb touches, the bottom of the bulb touches the negative side of the battery. I'm never going to be able to get this to work again. And the wire, come on, touches the side of the battery. Look at that. So this is 4. If I flip the battery over, this is what I did before, I also get it to light. So how can we use this knowledge of number 4 to give us some ideas, and your intuitions, because they are good, to give us some ideas about how current flows. So I'm going to pull us back to the front. All right, hang on, Ben. Okay, so I like Ben trying to start to think about this. Whoops, let me get us back in the middle. It's asking about a ground, and we'll get, whoops, that's not what I want either. I gotta make sure I'm in the screen for the recording. Okay. All right, so let's look at these ideas. Let's see if we can figure out what is going on. The first, these were your ideas. Something about being connected to the positive and negative side of the battery. You said something about a full circuit. I think that's a good intuition also, and something about the importance of the base of the bulb. So now one of Ben's comments that just got brought in is, well, does the side act as something? Let's see. Needs to be connected to two different places. I like it. Nice thinking. All right. I love how we're wrestling with these ideas. Perfect. Keep them coming. So let's redraw 4. So 4 had our battery with the bulb. So here's our bulb. And a wire went like that. And then I flipped it over and I had the positive end of the battery. Here's our bulb. Better. And the wire went like that. Now, one thing that'll help us, so first thing was important. The battery has a positive end and a negative end. Positive end and a negative end. 2 ends. And as was just suggested, maybe there needs to be 2 ends, 2 places on the bulb as well. Okay, hold that question about the wire, and we'll come back to that. So, 2 ends are important. This idea of a full circuit, that it can flow in and out, that it has to make a loop. We're all really good intuitions. So what's the deal with the bulb and one end being the bottom and one end being the side? If we were to take this bulb and look inside of it, so I'm going to make it big, we would find that the way a light bulb works is there's a wire that's touching the bottom of the bulb. That wire goes up. There's the filament, and it also touches the side of the bulb. So what the light bulb actually is, a light bulb like this, a filament bulb, is we have this wire that helps us in that complete loop. It comes, the bottom of the bulb has the wire attached. The electricity flows through the filament. This filament is what glows. So as electricity current flows through this filament, it loses some energy a little bit. And it's reduced to light, makes it light. So this filament glows. But this is called a resistor. We'll get to that in a minute. And the electricity continues to flow out the side of the bulb. So that metal screw part is metal for a reason. If you take any one of your light bulbs, they're all metal on the side, the little screw in part. That is serving as part of the loop. So that this then goes to the battery. And we have our full circle. We have our full circle. Now, one of the questions was, does it have to be physically touching the battery, or can it be through a wire? Either one works. And the reason for that is, in order for us to have a circuit that works, a complete, full loop, whatever word you want to use for it, a complete circuit, we have to have a very important element. A continuous line of conductors. Now, why is this important? Well, it's the conductors that the electrons can flow through. And so in order for those electrons to flow, for us to have a current, a flow of electricity, they have to be able to flow completely through the circuit. And we can only do that if we have conductors, a complete line of conductors. So the bottom of the light bulb is a conductor, and the side of that light bulb is a conductor, and we flow through. Okay, see a question pop up. Yes, so Ben asked 2 questions, or kind of question of why does the light bulb go out? The filament
loses its ability to reflect, and it also breaks. Two things can happen. So a lot of things can happen, but it has a lifespan of that filament. So what causes the filament to glow with that energy is what's lost. In addition, if there's any break, so sometimes when you see light bulbs, you see that filament break. How might a filament break? Well, it could break because of violin, it got shooken and it broke, in which case we would have a break of electricity. Or if too much current is put through the circuit, if there's too much of a potential difference, when we talked about that potential, if that's too much for this filament material, too much energy is being provided to that filament material and it can rupture. And that's when you see light bulbs go spot out like that. So good question, Ben. All right, so for a circuit to work, both of these things were good. You have to be connected to both ends. Now you were deducing the battery, awesome. But it turns out that every electrical device has two ends that we have to pay attention to. Not necessarily thinking about them as a positive or a negative end. The light bulb doesn't have a positive or a negative end. Battery does, and we're going to talk about why that is. But there are always two ends, an in and an out, for the electricity to flow in to that electrical device and to flow out. And the full circuit has to be a complete loop, a continuous line of conductors. So I'd encourage you to go back and look at those how to light up, the light bulb pictures, the 9 that were there, and see how the ones that didn't work, which was all of them but number 4, were either not a continuous line of conductors or they weren't using both ends, the in and the out. So some of them were still continuous lines of conductors, but they weren't using both the in and the out for each device. Now, the one that I kept mentioning is going to get warm is when we connect a wire from the bottom to the top of the battery. That is indeed a continuous line of conductors, and there's only one electrical device, and so it's going both into the in and the out. So electricity did in fact flow in that case. It didn't flow through the bulb, so we didn't light the bulb, but it did flow through the wire, and that's why it heated up. The wire is resistant to that electricity, but not great, and so it was getting warm and warm. That energy was causing the wire to become very warm. It's also draining or using the chemical energy of the battery. All right, I'm going to mention just a couple more things about devices, and then on Wednesday, we will not get through conductors. It's on your concept list. It says time permitting. We won't get through those. But I do think we'll be able to cover series circuits and parallel circuits on Wednesday. We're going to introduce those ideas today. And it'll probably just be in the first 20-25 minutes of Wednesday. I'll have a couple breakout rooms to practice all of this stuff, and then we'll have time to kind of review for the test. All right. Questions on this? Any more questions? Great ideas, great thoughts. I love the continuous thinking. Awesome. I'm going to introduce some vocabulary for us, and then we'll be ready to tackle sort of electricity in circuits on Wednesday. Okay. All right, if outlets have an inflow prong and an outflow prong, why is it necessary to have a ground prong? And, okay, all really good questions. Okay, so the ground prong on some electrical devices allows, I want to describe this. So it's a safety feature to, if there's a surge of that electricity, it allows that to go into the true ground. So when we talk about the ground, a grounding wire, whether it's on like a lightning rod on your house, or the ground prong, the rounder prong on an electrical device, it's a little bit of a surge, high energy protecting device, okay? And so part of the reason for that is because the ground, the physical ground, can take up a lot of electrons. And so with all those, we use the physical ground, we hammer things into the physical ground because that can dissipate the electrons widespread. And so it's not an additional port, it's a sort of a, it's the minus port, but it's the safety minus port. That's not a great explanation. Let me think of a different way to explain it. I want to get to our idea of voltage potential or voltage resistance and current before Wednesday, so I'm going to come back to you on that one, Ben, just to try to come up with a better off-the-cuff way to talk about it. Okay, I love the questions, so they're all really good questions. Okay, so the electrical devices that we're going to deal with, light bulb being one of them, battery being one of them, wires being one of them, are going to be more generic in the sense. So the battery is our source of potential energy. Okay, so this is our source of potential energy, and we normalize that energy, and we call, well, that's what we refer to. Voltage is the normalized energy. So like we talked about the normalized, when did we talk? Density was a normalized way to talk about things. Voltage is a normalized way to talk about this. So it's a measure of the potential energy within a circuit, right? It's typically from a battery. Now, it's not always from a battery. Sometimes we have a power source, so you might plug into your speakers, have a little power source. Your computer, of course, has a power source. We're going to do things with, we're going to think of a battery. So this is the how much those charges have been separated, okay? And if those positive, we have a positive end, which is represented by a long line, and a negative end, which is represented by a short line. So the positive end of the battery and the negative end of the battery. And if I have a large voltage, I've separated those charges. We can visualize it in distance. In a battery, it's a chemical way that we get potential. What you can think about it is that I have a big potential. So those positive charges, those electrons really want to flow from that one side of the thing to the other. That potential field that we've generated, it's really big, so the charges want to really flow. And I can get more flow of charge with a larger potential difference. Same with potential energy, right? Same idea. And we can get more electricity flow, which the actual flow of electrons is what we refer to as the current. Now, I always have very clever students in this class. We typically talk about electricity flowing from positive potential, high potential, to low potential. So when we talk about the energy flowing, if I have a wire coming out of a battery and going into a battery, like our two ends with our battery setup, we talk about the current flowing in this direction, from positive to negative, from positive to negative. That's how we're going to talk about the direction of current. Now, always have clever people in this class who say, wait a minute, if it's electrons flowing, why are they heading towards the negative plate, the negative side? Wouldn't they want to go away from the negative side? And you are absolutely 100% correct. They would. So in reality, it's kind of a fun little fact. In reality, even though we describe current flowing from positive to negative, it actually physically flows from negative to positive because it's electrons. But when current, and Ohm is the gentleman who helped us identify all of these things, when he was identifying the rules that govern direct flow, electrical flow, we didn't know that it was the electrons. They actually assumed it was the protons, the positive. It was positive charge flowing. And if it's positive charge flowing, then heck yeah, they want to get away from that positive end and go to the negative end. Well, we know better now. Unfortunately,
We never changed it. So it is the flow of electrons, but we define the flow in the direction positive to negative. High potential to low potential. So just keep that in mind. So current flows, how we describe it, from high potential to low potential. All right, and that's consistent with all the other stuff, our fluid flow, our pressure flow, so at least that's consistent. Now the last element that's in a circuit that we're going to talk about is our light bulb. Something that causes resistance to flow. And that is our resistor. So it's the light bulb. And oftentimes we'll put a circle around it to represent the light bulb idea, but it's represented by this wiggly line. And that is the last element in our circuit. And it is truly something that resists the flow, prevents the flow, causes a drop in potential from one side to the other side, uses the energy, okay? In the last couple of minutes, I want to relate these ideas together and talk about how electricity flows, and then we'll do the different types of circuits next week. So we said that current flows from the positive side to the negative side. Step number one. Current, positive to the negative. And that means high potential to low potential. So the potential across the resistor is high at the top, low at the bottom. It's connected to the positive of the battery, so that makes sense. This side's connected to the negative battery, so that might make sense also. But voltage drops across a resistor. All right. And how much current we get depends on both of those things. If I have a large potential, I can get a big current. If I have a large resistance, then there's a lot of resistance happening to that current. My current goes down. And we are out of time. But that is a relationship that Ohm discovered, that the potential is equal to the current times the resistance. So this is what's known as Ohm's law. And it tells us the bigger the potential difference for a given resistance, the higher the current. For a given potential difference, if I have a big resistance, I'm not going to get much current, right? So this is that relationship idea in a way similar to like Newton's second law we talked about, and some of those little impulse relationships, the idea of relationship, not causal necessarily. All right, we will do parallel series circuits on Wednesday and how those affect the current and the resistance very, very briefly. And then that'll be it for electricity. Okay, I will stick around to answer any questions or concerns about things, and your stuff should be up by later today for practice. Okay, I'm gonna stop recording.